Everyone, welcome back. In this video, we'll create synthetic CT projection data, what's called a sinogram, using a 2D fan beam geometry. This is part 1 of my CT reconstruction series, where we start from raw projections and later work up to full reconstructions. A CT scanner collects X-ray shadows from many angles. Instead of directly seeing a cross-section, the scanner measures line integrals of attenuation along each ray. When you stack those measurements by angle, you get a sinogram. That sinogram is the starting point for filter backprojection and iterative reconstruction. We'll use a Shepp Logan phantom scale to represent a human head about 240 millimeters in diameter inside a 300 millimeter field of view. The source we simulate 570 millimeters from the rotation center. That's the source axis distance. The detector is an arc 1040 millimeters away from the source, which is the source to detector distance. We simulate 512 detector beams covering an angular span wide enough to capture the object, and will collect 720 views over a full 360 degrees. Now let's quickly talk about the ray geometry. Each detector beam defines a ray that connects the X-ray source to that detector position. Mathematically, we can describe the ray as a line starting at the source point and extending through the detector coordinate. As we trace along that line, we sample the attenuation map. Summing those samples gives us the line integral, which is exactly what the scanner measures for that ray. Now let's go to the code for generating the sinogram. Here are the parameters we simulate in this simulation. We use 512 detectors over 720 views spanning 360 degrees. We start with a Shepp Logan phantom, and we scale it to realistic dimensions. Then we use ray tracing to generate the line integrals. And here is the fan beam geometry. We define the source position, and also we iterate over each detectors for each angles. And then we generate the line integral along that ray and make up the sinogram. We save it in a projection file, which is a raw data, and we can view it using ImageJ. So now let's run the code. It will generate a projection file, which is 512 detector rows and 720 view angles. And when it's done, we'll use ImageJ to view the raw sinogram data. One note is that the way we are coding this right now is educational, and it runs entirely on the CPU, looping over detectors and views. In real CT research, this forward projection is highly parallel, so we can often accelerate it using a GPU algorithm. That's how you get from minutes down to seconds. So now it's done. Let's use ImageJ to open the sinogram. We use the import raw option. And this is the one we just generated. We open with 720 width, 512 heights indicate the number of views and the number of detectors. We use Little Indian byte order, and we say OK. And here you see the beautiful sinogram. And each in this dimension is the detector dimension, and here in this dimension is the view angle dimension. So this concludes part 1, generating realistic fan beam sinogram data. In the next video, we'll reconstruct the Shepp Logan phantom from this sinogram using filtered back projection. Make sure to save your projection file. We'll need it for part 2. Don't forget to like and subscribe if you want to follow along with the rest of this CT series. Thank you for watching. See you next time.